So originally we had Professor Mickey Ladd of Technion to give a talk, but due to last-minute complication, he couldn't join. We're planning. I'll be as a backup speaker for him. So hopefully that will be equally entertaining. So this is a talk I have given recently. I think when I visited the MBZUAI, actually I gave a similar talk, but today I probably give another version and with some of the latest progress. Right? As you can see, that this is a sort of a reflect some of our recent, in the past 2 or 3 years, our reflection on what is behind the deep learning, what is behind artificial intelligence, or intelligence in general. Right? What are the computational mathematical principles that may be providing some kind of governing or unifying views or explanation to what the practice of artificial intelligence. And also you can think about this as a continuation of very complementary to the lecture I gave on the tutorial day, the first day, where we talk about how do you use a sort of a measure of information game to deduce deep networks from first principles. But there we actually talk about how to do this in to learn the features, right? Learn representations. But how do you know the deep network plays a role as optimization? But the question is the optimal solution may not be the correct solution. Right? In order to ensure that the optimization process, the deep network give you the correct representation, you need an additional mechanism to ensure the representation is correct. I will be clear about by what I mean by that in a second. Right? So continuing from the start, right? We had the tutorial, the first talk, is that the one way everybody talk about, we try to understand deep learning. We try to understand what's going on, right, as a black box. So in the past 10 years, a lot of the theoretical study has to be study the deep network itself as the object of study. To me, actually, that's not necessarily the right thing, right? So maybe one question we should ask is what the learning is trying to do. Right? If we are clear about that objective, maybe deep networks, all its manifestations, all its different versions, variants, are just the means to the end. Right? We can have a much deeper understanding what's going on. Right? It's more. So we try to backstep a little bit. What is the learning trying to do? Right? I elaborated a little bit on in the previous talk. So then we try to highlight it. Then one thing we actually find out that maybe almost all the learning purpose is trying to build a model for the world from our external visual data or audio data or the sensorial data, right? A learned structure represented in a very compact structured way so that we can use the learned as a memory to predict what's going to happen, right? Hence, we call this parsimony principle. How to build a compact structured model of the world. The central question there, how do we measure that? How do you know the model is good, right? So there's the measure of goodness, and we'll introduce that briefly. And then the focus of today is that, I talk about the first part a little bit more during the first lecture, but today I'll focus on the second thing. If the network is trying to optimize the representation, but the optimized representation may not be the correct representation. All right? That's completely two different concepts. Optimal solution is not necessarily the correct one. Right? Now, how do you ensure the correctness? And that's the second principle. And we'll see how an effective computational mechanism can ensure that. Right? You can even think about some of the mechanism people do, like backpropagation, is kind of ensuring that, but the nature may not be able to have the luxury to do that. Then what additional mechanism, probably more effective, more efficient mechanism allows you to do that. That's what we call this, how to ensure self-consistency. Right? As I said, some of you, if you attended my previous lecture, you probably know this, right? And we try to do things in a very deductive way. Right? We start with the assumption our data maybe belongs to multiple classes, multi-model data, right? Multiple low-dimensional structures, right? Each class of data, each class of images, apple belongs to a low-dimensional manifold. Orange is another manifold, right? maybe, this is an apple, this is an orange. They're sitting on this manifold, sits on a million dimensions, right? If you have a picture of a million pixels, every picture is a dot, right? You have a collection of those. Now the question is, we see all this image, we get bombarded with images and videos. What our brain is trying to do? We try to build a very compact structure model for it, right? We try to sort them out. Now, how do we measure compactness and the structure? We'll get into that in a second. Right, in the sense that this is why deep learning was successful in the first place. It is seek a very simplistic model, right? We have multiple class of data, right? We try to map each class into a singleton, into a one hot label, right? I think there's quite a few lectures at the tutorial talk about that. This phenomenon that you try to collapse all the data in one class into that one singleton, right? This is a so-called neural collapse phenomena. The way to do that is try to enforce the map that you learned, the deep network. I think it's running out of, I don't have the F, to be able to, the output to mostly closely correlated to the one hot singleton, right? One hot label, Y. There. This pointer doesn't work. Can someone, I think the pointer is out of battery or something. Do you have another pointer? Yeah. It's very hard to move, right? In fact, I would argue, if deep network hinted they choose a different output representation, it won't work, okay? So the very reason, yeah, do you have a pointer? Which one? Yeah, it is, but it doesn't work. Yeah, it's running out of battery. Yeah, do you have another pointer? Okay, good. So this is one thing, right? So the question is that but collapsing all each class into one singleton may be good enough for classification, right? You can get a very good classifiers, as many things that people assume. But what if I do something else? Our brain is not just a classifier, right? We recognize apple not because we recognize this apple. We actually close our eyes, we can visualize what an apple looks like, right? What if you want to go back to regenerate the data? Sort of this, generative model, right? How do you do that? So hence you don't want, does anyone has a pointer? It's very annoying. Anyone has a pointer? So you do not want this collapse to one subspace. For example, all the image of apples, right? There may be 10 attributes, spans of 10-dimensional manifolds, right? You want to map that to a 10-dimensional subspaces, right? Rather than a one-dimensional singleton. Does anyone has? This is coming back, come and go for some reason. Yeah. See, I think it's running out of battery. It's just come and go. Hello. Do you have a new one? This one definitely doesn't work. Okay. Huh? It does not work. Oh yeah, please. Yeah. Now, do you have the battery there? Can you bring the battery? Can you bring the battery here? Yeah, that will be better. I need to use the. Shoot. Okay, you don't have another pointer? Anyway, so good. How do we do with a physical pointer or something? Let's see if I have one. Do you have? Good. Yeah, just something. Yeah. This one works? Okay. No, there's doesn't have pointer. No, it doesn't. What? It doesn't have pointer. No, it doesn't. Okay. It's very strange. Yeah. Okay, good. So you actually want to make sure this mapping is 1, 1, right? You want to make the most generative one, right? And so the question is, how do you go back, right? You want to make sure your model is actually faithful, right? The mapping is faithful, right? So, for example, we want to make if the original distribution could be nonlinear, but we try to make it linear, map the linear subspaces, right? Make it a very compact, standard, structured. Right? Now, once you do this, let's just formulate this a little bit. If this is what you wanted to do, you want to make the mapping 1, 1, and make it a standard model out of your distributions. Now, suddenly you realize, right, in order to make different classes, let's say orthogonal, apple, oranges are not intersecting, become independent, right? You suddenly actually realize that even you can, if each dimension, each class has a, first class has D1 dimension, second class has D2 dimension, right? In order to make them separately independent in subspaces, you actually have to have at least the ambient space for the feature space to be at least as large as the sum of all the individual subspaces, right? So the D will be larger than that. Now, if you wanted to do this, if this is something sensible to do, you suddenly realize that then the distribution, the feature for each class is actually embedded in the hidden, in the feature space, right? No matter how little D is. Hence, the feature will be hidden as a low-dimensional subspace or surfaces in that subspace, in that space. So therefore, if the structure, if those features, the image of the features in the feature space are not clear, it's that the cluster is still some curve, crazy curves. There's no way you can trace them. You still have to random sample to get them, right? So one thing to make that easy, you have to make the feature in the feature space distribution to be standard, very, very structured, right? So linear subspace become one of the natural choices, right? We want to make it linear so we can identify them. So now the next question is, if this is a class of model I'm trying to map all the data in the world into those mixture of subspaces. Which one is a good one? How do I measure the goodness, right? For example, if my data, like apple lies on one line, orange lies on another line, right? Left and right, they both says the two class of the images lies on the 2 lines, right? Intrinsically, they're the same model. But somehow we always prefer the left one, right? The image of the apple and the image of the orange are orthogonal subspaces. They're independent, statistically independent, or geometrically orthogonal. We prefer that. Why? Right. So there's actually a very good information theoretical reason for that, because the one picture on the left achieved the maximum information gain. What we mean by that is that if you don't tell me where the apple oranges are, right? They just span the whole space. I need, in order to find which individual image or each individual features is, I need to encode that entire space. I need a lot of epsilon ball to pack that entire spaces to tell me which location each individual feature is. But if you specify your data is on those blue lines, right? I only need the number of green balls to specify which location of each feature. The volume becomes much less. Therefore, the notion between the volume for the whole minus volume for the parts, this is a very fundamental quantity, right? A way to measure that. So then, of course, hence we're here trying to make the computable. We are just to use, or this is a continuous distribution. In order to make this, save the data on the digital computer, right? We try to quantize it. We use the epsilon ball to pack it. The number of balls, the blue balls, actually is given by the first formula, right? That's just the whole volume. You can think about log determined capture. What is the number of balls for that space, right? Yeah. Good, thank you. Yeah, thanks. Yeah. So this actually can capture what is it, still doesn't work. Anyway, I think. Yeah, so it's just a very strange. Maybe I can just point like this. You can just see a fraction of it. Yeah. So this is so this first one is actually capture how many number of balls, right? Logits of the log of that number of balls, volumes. The second is actually the parts, sum of the parts. Right. The difference is actually called this actually is a rate reduction. It's how many average number of bits you need to describe a feature falls into this region, right? The blue region. Right? The second one is just the how many number of bits you need to specify the green balls in that region. Right? The difference, what we call, is actually we call the rate reduction. It's kind of the number of coding rate for the whole minus the coding rate for the parts. Right? You can think about this as kind of measure for information gain. Naturally, you want to maximize this. Right? So you want to get maximize your information gain. So that you get you prefer the left representation rather than left. Now, what's good about this? Right? This is actually a formula. So this is actually assuming your data such a piecewise Gaussian, piecewise linear. You can actually measure this very accurately. This is a closed form. Compute very efficiently. You can compute this by computing the covariance of each matrix. But what's good about this? Almost everything we know about deep network comes from this formula, right? So how do? We want to optimize this thing, right? The one thing to optimize, remember, everybody, we try to do this, let's just compute the gradient, right? We want to maximize this quantity, we compute its gradient, we do gradient ascent, right? Well, as soon as you do that, you realize this is the formula for the gradient, right? This actually has two interpretations, if you wish. One, you can interpret this inverse matrix. By the way, this formula is exactly the residual, right, of the using data to auto-regress each other. And this is the residual from that. And you can interpret this inverse matrix as a linear operator acting on the feature. And this is precisely interpreting this as a residual network. And now, if you say, I just do volume and expansion of the inverse of matrix, take the first order term. That's exactly the terms shows up in the self-extension transformer. Right? Basically, what this is doing is very, very stupid. Right? I try to compress each class, making each class, this distribution become a subspace. I try to squeeze it, linearize it. I compute the volume. Right? If it's not linear, I can squeeze it. So the gradient just tells me which direction to squeeze. It's most effective. For different classes, I want to expand them. The residual tells me directions, in which direction I expand is most effective. That's it. But interestingly, both have exactly the mathematical form. It just matter of put a positive sign or negative sign. You're expanding, or you're contrasting, or you're contracting. They're exactly the same mathematical operator. Residual network, transformers are doing exactly the same. Just who is more accurate. Now, suddenly, once you realize that, right, you actually can derive the network as just a means to achieve optimization, to do compression and expansion. Nothing more, nothing less, right? Since the inception of deep networks, right, all the practice deep network has been on the left column. Try to fit some input-output relationships. And the net architecture is tried and tested, right? You design in a very empirical way, right? You augment the data. You randomly initialize carefully, right? And you do backpropagation to optimize, right? After you're done, you get a black box. And you spend millions of dollars training a big model. In the end, the feature, still you call it latent or hidden, which is somewhat ironic to think about it, right? Now, once you know if the object function, if the network, if we are trying to optimize the whole representation learnings to maximize the information gain, everything is upside down. Right? Object function becomes information theoretically rigorous. Then the network, each layer, ResNet, transformer, every layer is trying to do iterative optimization to make the information gain better and better. Right? And each layer is doing projected gradient descent. Itself, not optimizing the neural network. Network itself is doing optimization, layer by layer, iteration by iteration. Okay? That's very different from how you train neural network. Of course, you can train, if the forward iteration unrolling is not good enough, of course you can fine-tune it. Nobody can stop you from doing that. Just like, Yann-LeCun optimized Lista, give a more effective algorithm for a recovery sparse solution. It's the same idea. Right? And the good thing about it is this network, all the architecture, a white box. You know exactly what each layer is doing. Mathematically, they're completely transparent. every parameter, right? And in the end of the day, you get a representation which is also transparent, independent subspaces, compact standard structure. So as engineers, I like this because as a control engineer, we know that, right? Any system, before we control it, before we compute it, what do we do first? If it's nonlinear, we linearize them. If they're not standard, we standardize them. This is exactly the same procedure. I'm pretty sure our brain is doing the same thing with the complex world we perceive. Right? Does this work? Yes, it starts to work. Right? In the very beginning, people say, when first time, Alex-led the residual network comes out, people actually believe it's doing sparse deconvolution. It's doing some single processing problem, right? But people tried. Let's design neural network with some, sparse deconvolution. It doesn't work. Hence, we believe those neural networks has something mysterious. Hence, we do auto-LAS, auto-ML to search for something even more wonderful. But after 10 years, only 2 networks survived, ResNet and Transformer. And both they're doing gradient descent for compression, right? That says a lot. Now, does the principle using sparse or pure deconvolution, a white box design works, can really scale up, compete with the best network in the world? Yes, they can. Principle always work. This is our latest work in NEPS. We call it revisiting the sparse deconvolution models. You just build each layer using sparse deconvolution, right? The performance is as good as ResNet, and the impact is even better. Much more small, compact, and it's more stable to noise. It's a good lesson, guys. Principle always work. But you just have to implement it correctly, okay? Now the question is about one end, right? What about we want to also make the mapping? As I said, the forward optimization is only give you optimal solution, maybe get stuck with local minima, may not even converge. How do you know the Z, the feature you converge at, is actually good enough? You actually can recover X authentically, right, faithfully. You need to build the reverse map. You need to go back, right? Now, there's nothing new under the sun, people, right? This is a problem we have been doing for hundreds of years, right? Because a simpler case, when the data X, each class is already on a single subspace, it's called a PCA, right? You project, you lift, right? And of course, the real distribution may be nonlinear, which is called the nonlinear PCA, by the way. The first paper about it, there's another name to this, which is exactly called autoencoding, named by Hinton. Right? It's just a nonlinear PCA. Of course, the real-world data may be multi-model, multi-class. You have multiple subspaces. In the case of multiple subspaces, we call it a generalized PCA, as Renee and we did it. Wrote a book about it. Of course, the real-world problem is not as simple, right? The real-world problem is actually maybe dealing with multiple nonlinear manifolds. Right? We need to make it real. Right? But how do we make it real? Right? Works for multiple nonlinear manifolds. Maybe we can learn a couple of things from simpler cases. PCA. Right? How do we do PCA? Everybody knows. Everybody in this room should know, right? We learn linear projection. We lift it back. Make sure after you project, lift it back, they're closed. X and X hat are closed. Everybody knows this, right? The high school stuff. This is easy to do because the mapping is linear, right? And also you can use the 2 norm, X and X hat. As long as they're closed, you're done, right? There's an almost closed form for this, SVD, using SVD. But the things get a little bit tricky if you're dealing with manifold, especially image manifold. Why? First of all, this mapping has to be, you have to linearize the manifold, right? Make it linear, and then the F cannot be linear anymore. It's some nonlinear mapping, you don't know what it is. This is actually not the hard part, by the way. The hard part is that, well, you want X and X hat to be closed, right? But that notion of close is no longer because you don't know the manifold. What is the distance between 2 manifolds? Right? Information, the image processing, computer vision spent 50 years studying this problem. Why? You can no longer use 2 norms anymore, right? Two norm is bad. Why two norm is bad? Because the same image, if I shift it to the left by a couple pixels, two norm changes a lot. But it's the same content. If the same image, if I blur it, our two norm changes a little bit. But everybody suffers, right? I think there's a big perceptual differences. So two norms is not good. So how do we do that? What is the right distance between the two distribution of images? That's actually the holy grail, right? We try to get hold of that. Well, I don't know, right? So people, to begin with, I don't know how the distance, but you have to tell me something about what the image distributions are, right? So people say, tell me how the image, maybe if there's some knowledge about how the image were generated, some probabilistic model, maybe I can put a probabilistic distance, right? The distance between the two distributions I can evaluate, right? How to do those? I don't know, right? But let's say, suppose we even have this. Suppose we even know how the image were generated, right? Computing the KL divergence, computing the maximum likelihood is intractable, by the way, in general. Especially when the distribution with the natural image is degenerate in the meaning space of minimum dimensions. This quantity is not even well defined. You cannot compute it. You can talk about it, but can never access it. Right? Now, what do people do in reality? Let's approximate, right? Let's do some variation on lower bound. Turns out this lower bound is not that easy to compute. You have to come up with some surrogate for the posterior, and a lot of times you have to approximate, right? That's why there are thousands of papers, because everybody's proposed a different way to approximate them, to sample them, to evaluate them, and everybody try to convince other people mine is better than yours by showing a few examples. So you know that after a while, this is actually about 40 years of study in computer vision, in image processing, right? The people like Irv Granander, David Mumford, and also Songchun Zhu, and their fourth generation called Zuowen Tu, right? He's a professor at UC San Diego. He said eventually he gave up. The generative model doesn't, the generative approach doesn't work, right? Can we learn generative model using discriminant approach? That's his 2007 CVPR paper. The idea is exactly the GAN. Okay, later on people gave a fancy name called the GAN, right? Right, become very popular. It says that I don't know the distance between X and X hat, but maybe I can learn some discriminator. If the discriminator cannot separate them apart, maybe they're close enough, right? The very simple idea, right? Then they formulated this as a game, right, with cross entropy, like that. Turns out this is actually a fake game. It's not a real game, because this is exactly equivalent to minimize the distance called the Jensen-Shannon distance, right? It's a minimization. Again, it's minimizing the two distance. What's the difference, right, between minimizing KL divergence and the challenge? Actually, conceptually very minor. Only that when KL divergence, two distributions doesn't have overlap, it's not well defined. But for Jensen-Shannon distance, it's well defined. But it's still not computable. Okay, it's intractable to compute for general distributions. Right? Why? Because when you're dealing with high-dimensional distributions in high-dimensional spaces, low-dimensional distribution in high-dimensional spaces, if the distribution doesn't overlap, do not overlap, which is always, always, always the case. Don't argue otherwise, okay? I have worked on this for 30 years, right? So they never overlap. Hence, the distance actually behaves like L0 norm. It's well defined when the overlap become. So basically, you actually minimize things just like an LO norm. Of course, in practice, you can approximate, right? Sample, approximate, using other surrogate. Replace Jensen-Shannon with a W distance for the Earth mover, right? So it really looks like an L1 norm now, just like we use L1 to approximate L0, similar to that. But turns out that the Earth moving W distance is not computable either. Then what do people do? We further approximate. So after several layers of approximation, I really don't know what you're doing. Fine, if you have 5,000 GPUs, you can approximate, you can sample, you can optimize this in a brute force way to get very fancy results. But fundamentally, this does not change the fact the problem is intractable. This is not a new solution. It's a still old solution. You just restated the same problem. Okay? So there is a case where we can compute efficiently. between high-dimensional distributions, which is that case, which is a mixture of Gaussians or mixture of subspaces, right? So this rate distortion, right? This rate reduction gave you a measure for that between two subspaces or multiple subspaces, arbitrary classes. But don't get me fooled, right? This is the only case you can have a closed form for such a distance when the distribution is a mixture of Gaussian or mixture of subspaces. But the original data, X, are not Gaussians, are not subspaces. Now what's going on, right? Just recap, right? We try to measure the distance between the original data and the regenerated data X hat. But the distance is very hard to get. It's in general very hard to compute, expensive, right? Yes, if we're lucky, if we can map X to Z, if Z are piecewise linear Gaussian, this can be measured very, very efficiently, right? But there's a dilemma, right? What I care is X, but you tell me to measure Z. How can I guarantee something good for Z will be also good for X? Now, there's an even more fundamental question. How did we do it? How did the animal do it? We never, ever measure anything in the data space. When you grow up, do you carry a ruler in your pocket? Every time you tell us how big size of this, am I wrong? You never do that. But how did we give a very persistent, accurate model for the world? We do everything internally. We never compute in our retina. And also, we cannot afford backpropagation either, right? The most recent paper from Hinton precisely said that. Nature cannot implement backpropagation. Everything's forward. But there is one way. How can we guarantee our solution Z is accurate? There is a universal mechanism, actually, right in front of us, right? You close the loop. You use loop to feedback, right? So this is a fundamental idea, right? So in order to compare X and X hat, right, I don't have to compare them directly. I map them in together, all inside in my brain, again, right? Goes through the same feature mapping F map to Z, then X hat maps through the same F map to Z hat. I only have to compare Z and Z hat in the feature space. There I have everything in control. I can count the bits, right? Everything is computable. I want everything to be subspace, everything to be standard, right? Now, so that's actually basic idea, right? You actually only compare here. This is an encoder. This is Z is a generator, right? In order to compare those two, you map to the image. You make sure there's no difference between here. Right. But just minimizing Z and Z hat is actually not enough. Why? Mathematically, right? Even if Z and Z hat are the same, does not necessarily mean X and X hat are the same. Because F maybe kill something, right? So this is therefore, F has to also become a self-critic. F have to adjust its parameter to see if there's a remaining difference between X and X hat. That actually make the generator and the encoder F as a mutually self-critic each other. But there's a natural game mechanism going on. Right? F is trying to identify the structure of the data. G is trying to recreate the data. Of course, both can be wrong. They self-correct each other. So G is trying to minimize the difference between Z and Z hat. F is actually trying to maximize, see if there's still remaining error in it. It makes G is minimizing, F is magnifying if there's a difference. Until this is done, F cannot separate, right? Which really means the blue curve and the black curve, the two distributions match perfectly. This is a pursuit evasion game. This is a real game. You cannot reduce to a minimization or maximization. Right? And this is a mechanism, actually, I argue, would be universal to actually check if your model Z is actually consistent to your observations. And this is the way, and once you have this mechanism, the learning can be fully autonomous. You don't need any supervision. Just like our animals, right? So another interesting thing is that once you realize that, let's put together, right? So remember, we want our x and z to be the same. The z and z hat to be the same, right? So all the measurement, if you see that, shoot, what's going on with this? Right. This is actually just so this is actually remember when we learn the radial reduction, right? We want each class to be orthogonal, right? Each class to be linear, different class to be orthogonal. That's exactly by the first term, right? That's the delta R. It's trying to do expansive coding, make sure different classes expand, each class become linear. This is to make sure the closed loop, after closed loop, x, z, and z hat are the same. And this term is actually make sure when I do decoding, I use the minimal resource. The G only want to decode X up to the point that F cannot tell them apart, right? Try to minimize. Hence, you actually can see that when you learn the representation, what similar gets compressed, what's dissimilar gets expanded. And also, the correctness gets guaranteed by this closed loop. Every term here actually just measure the cracks between those subspace on the right. Blue, between those black lines, blue between black and blue lines, and so on. Nothing more, nothing less. And measure them in terms of bits, in terms of how many balls you can pack in between. Very basic. Everything is doing counting, right? Bin counting. Human decides nothing, except maybe the size of the ball, how accurate you want your information. Then that's it, right? You can see this is an object function. Human decides nothing. It's completely objective, right? Every experiment you see from now on optimize this term. No heuristics, no hacks, not even weights, right? Just directly optimize them. Everything is a closed form, right? It's closed, and what you learn is structured. Suddenly you start to realize that to learn distribution of high-dimensional data, you don't need priors, specify any priors. The only assumption is that they are low-dimensional. Second, right, you don't need any explicit heuristic between x and x hat. You don't need to touch x. You just have to observe it, right? No more approximation for all the KL divergence, Jensen-Shannon divergence, WDCs, they're all gone. Nature don't know them. Nature doesn't know those distances, okay? Don't even know how to approximate them. They only know counting beams. Right? And does this work? Yes. Works remarkably, right? All the experiments, we try to get all the public data sets. And in fact, we don't fine-tune anything. We use the same network, very simple network. All the hyperparameters are the same. We don't even tune them. We don't customize for each network. The same feature dimension, same hyperparameter for all the experiments you're going to say. Already, this gives you a generative model. Better than VAE, better than GAN, right, in terms of visual qualities and so on all the data sets, CFAR, MList, and ImageNet. Not only that, you get more with less, right? You don't just learn a hidden representation, you random sample to generate. Each class is a subspace. It's highly organized, structured. And you can compute the PCA for each class. Right? You sample on each class. It's much better controlled than InfoGAN or ACGAN, even on the simple data sets like MList. And you get a classifier. Unlike GAN, right? Only generate data. This actually you get a classifier because you have the PCA, different subspaces. You just do your subspace classify. You compete with the VAE algorithm. And a different mode, different rotation, just become different principal components. Human decides nothing. Right? This is on CFAR 10, right? Each class, we compute the principal component. Each class becomes a subspace, right? In a feature space. I compute a PCA, I sample along that PCA, I regenerate image, right? Each row you see from a different PCA, from a different direction. Right? It's organized, very diverse. Right? No mode collapsing. And you can see the capture mode. Hence, there's all the argument in machine learning. Oh, disentanglement is hard, impossible, maybe can be done, may not be can be done. Disentanglement is easy if the data stipulates it. Right? Different classes become different principal subspaces. Different attributes becomes different principal components. That's it. Human decides nothing. You don't try to say, oh, this attribute might be able to, I have to stipulate this surrogate, right? Those two might be independent. Maybe not. No, you don't get to do that. Right? For example, human faces, right? Here we don't distinguish different identity. We just treat them as one distribution, one subspace. We map them into one subspace. But this is the first principal component. This is the encode data. This is the output data, right? Can you see what's the dominant principal component? Character changes, right? But something don't change. The pose. The pose becomes the first principal component of your face if you encode faces. Okay? What about the other principal components? Maybe the nice one. Turns out the nice one just become everybody wearing sunglasses. What about 23? 23, everybody become a hat, wear hats. You don't have to random sample that space, cherry pick two samples to do the morphing. No, you don't. It's just PCA. Everything linearized, structured, right? And then people tell you our training gang is very finicky, very often you have to be very careful, right? Doing the mode collapsing. Closed loop is very stable. It's very hard to collapse. You do end-to-end, yes, it's very... Now, what about, this is supervised. I need to know 10 classes. I need to label, right? I need to compute the rate of hierarchy. What if the data is not labeled, right? What is one class at a time, right? We don't learn, human being, we don't learn 10 classes simultaneously, right? We learn one class at a time, right? One English word at a time, right? It's incremental, continuous. But we all know if you train an open-ended, end-to-end deep network, if you retrain for new classes, there's a phenomenon called the catastrophic forgetting, which means if you learn for 10 classes, learn new 5 classes, the network going to forget about all the 10 classes it had learned just now, right? Closed loop never forgets, right? It actually works precisely. You just give one class at a time. You get double digits improve with a much less memory footing, with a much smaller network, right? No catastrophic forgetting. In fact, if you show the same old class to the loops again, the model gets better and better. It naturally has that's exactly what we do. If we see the same English word better, we remember it better, right? It's called a consolidation. The closed loop network has exactly this property. It consolidates. What if I don't even have class, right? Apple, orange. The image is not even labeled. One image at a time. Actually, as kids, we learn that way, right? We don't even know the class. We saw apples, orange, once at a time. No problem. Every time you just treat the new image as a new class, the closed loop just had to remember it, right? Nothing changes. Exactly the same quantity, the same architecture. One image at a time. It works. Actually, it gives the best unsupervised. Compared with Moco, Sinclair, actually this works better. This is our recent work with Yang Kong's group, right? Not only that, see, I have no labels on CIFAR. I trained the no labels on CIFAR, but the block diagonal shows up. If their images are similar, those kind of block structure similarity shows up in the image. Why that is the case, we don't know. Right? And you can see the feature, right, learned by this closed loop transcription is much more clear in terms of local structure than this is from Moco's V2, some of the latest unsupervised learning method. Really preserve those low-dimensional structures. And this is actually still work, right? We chose F and G as just generic neural networks, right? ResNet or something, very simple, right? Or DC-GAN, whatever the simple network, convolution network. What if F and G, just like in the first, we replaced them with some white box design? Completely just the convolution, deconvolution. Actually, that works even better. This is our recent work, right? Some of the poster shows the results. In fact, compared to the diffusion, right? What we're trying to do is exactly opposite, right? Diffusion is trying to map the distribution of image to some random, through a diffusion process, to some random spaces, then go back, right? Well, fine. That's one way to get access of distribution. But what we're trying to do is we try to standardize, make the distribution linearized. make it structured. We're doing structured diffusion, denoising. Okay? And this is actually very striking. This is some of the things that you can do this purely white box, nothing hidden. Everything you design, the F and G, every layer you design by convolution, deconvolution, right? Give you very striking, this is an entire image net with only a 5-layer network, okay? Very tiny network, memorize millions of images, one by one. We start to see phenomena we have never seen before. With purely white box objective, white box network. No hacks, no heuristics, no guesses. Right? And this is on, and also if you train the closed loop system on the CFAR, it works on CFAR 100. Right? All the generalizability, just like a memory, like a hard memory. And if you know a little bit of neuroscience, everything we saw in this closed loop system, we observed that in the monkey, in the brain. Right? Sparse coding, subspace embedding. Right? Monkey remember human faces as a subspace, 200 neurons as coordinates. Not only that, they do predictive coding. Every step is closed loop. Right? And also, this is the real data from measuring monkey, memorizing 4 different categories of objects in a different part of the brain. This is a correlation of the signal. Does this look a little bit similar to what you do? It's complete unsupervised. Monkey see one image at a time. There's no labels, no categories. Monkey just memorizes them. And somehow, the monkey's brain remember different categories in that way. Different areas of neurons fires differently. They organize memories. That's what the brain does. Right? Hence, I wanted to argue, right? This is really something very, very fundamental, basic, right? The process from X and Z is trying to maximize the information. Now, the mechanism to do that is just closed loop transcription. This single loop already integrates the 4 key elements, right? We know. How to measure the distribution, the goodness of the representation is just information theoretical rate reduction, rate distortion, right? And the deep network, F and G, are just iterative optimization. You choose your favorite optimization to optimize that that objective function. But optimization doesn't give you something correct. In order to correct the error, you close the loop. Also, closed loop is not going to be enough, right? Because this is compressive. Make sure there's no error left. F and G has to be mutually self-critical each other. That's the game. You learn from the game. You constantly use your memory to predict if there's any error, you adjust. That's it. That's all you need. Right? They actually putting these 4 ingredients together, this whole learning process becomes autonomous. Right? There's tons, this actually empirically I already show you a lot of good results, right? It works very, very well, but there's tons of open problems. We know little about them, right? This is a game, minimizing, right? Equilibrium point. What is the equilibrium point? We don't know in general cases. And this is infinite. There's really a game between learning, control, chasing 2 distributions. In theory, that's an infinite dimensional object, right? How can you guarantee that's converged? We don't know. By the way, right, we're deforming the manifolds, right? Who says the redo network, the gradient descent or transformer is the best gradient descent algorithm? No. There's gazillions other choices. Sky's the limit. 300 years of designing optimization algorithm tells you how to design each layer better. We barely started that quest. Our brain only have about dozens of layers, much more effective than any deep networks. Right? And also, this quantity looks very simple, right? But turns out this is computing the ratio, when the ratio between the whole and the parts gets maximized or minimized. Right? Turns out that ratio has something to do with this Braskamp-Lib inequality, which is called the mother of all inequality. All the inequality you see in your life are just a special case of this, almost. And Terence Tao has a few papers about this, about 10 years ago, if you know. But just barely 10 years ago, people don't even know this kind of ratio has maximum or minimal. Right? It's very deep mathematically. And why this doesn't go? The only thing we know, I mean, there's a poster about this work. We are able to prove that when the distribution is already a mixture of subspaces, we are able to prove that the minimax formulation gives you a right answer. Right? This is the only special case we know theoretically. We can prove something about it. But the general manifold, nobody knows anything. Right? So, but the question about how do you scale up? We have a follow-up work, and how do you completely do white box design? There's still ongoing work. Now, by the way, here I just use the subspaces, right, mixture of subspaces to illustrate the idea of information gain. But if you are seeking different structure, causal structure, dynamic structure, or genetic structure, right? As long as you can measure the rate distortion, can measure the complexity of your distribution, can measure the information gain, you can apply the same principle, right? Our brain is a closed loop, our muscle is a closed loop, our DNA, RNA is also another closed loop, right? It's universal. But it's all trying to minimize something, right? So here, people like to, somehow in machine learning, people like to write papers, say, something is all you need. This picture just gives you a little bit of how small we are, okay? Right now, the deep networks we have, right? We think this open deep network is everything, going to solve all the problems in the world? No, absolutely not, right? It's just the 2 segments. It's just a process, right? Try to maximize from the input to output to maximize the information gain. But how do you guarantee it's effective? How do you guarantee it's correct? They're just 2 segments of a closed loop. Error correction. And also, one loop is not enough, guys. Our brain consists of a quarter of millions of cortical columns. They're parallel. Why? Robustness, efficiency, right? So you make them to build each column, you build massive of them, parallel or sequential. And also, once you can convert analog signal to something structured, you have a basis, you have a raw material for high-level concept. This subspace is an apple. That subspace, you can form symbolic computing. Without that, forget about symbolic computing, right? Structure is the basis for symbolic computing, right? But regardless, I argue that probably the entire brain, most of part of it, is every bit of it is input-output is trying to maximize the information gain, try to organize the information to perceive, right? Nothing else. Right, this is just a serious paper, right? So as I said, right, even in the tutorial I mentioned, right, many of some of the ideas from using coding lens, using rate distortion to do clustering classification trace back about 15 years ago, since we're dealing with subspaces, Gaussians, right? And really what links those Gaussian subspace cases that through a deep network, which precisely mapping that nonlinear mapping from nonlinear to linear. Nothing more, nothing less, right? Even the operator. Residual network, transformer are just doing that. And you wanted to do this in a closed loop so that and you don't have to pay the price for end-to-end. Okay, backpropagation with trillions of input-output pairs, right? Can do much more. Then once you have the closed loop, it works in all settings now, as far as we know it. Generative, discriminative. Supervised, incremental, unsupervised. They're all achieving state-of-the-art, even way beyond. With much less data, with much, much smaller network, right? And some of the foundation, right, with this work as a tutorial, actually characterized by, how do the sparse representation, seeking structure, compact structure, sparse structures, and through compression, through optimization, right, dealing with nonlinearity, sort of captured in this book. But I want to remind you people, everything I said in the tutorial talk and today's talk and in that book, at least conceptually, was already said in the book by Nobel winner back in 1948. Okay? Compact coding, closed loop feedback, linear via games, white box modeling, nonlinearity, shift invariant spring waves. I just want to remind people, right? 1940s is really the true origin of AI, cybernetics. Shannon published his paper. Von Neumann published his game theory paper. Shannon published the information theory paper. Robert Wiener published his book on cybernetics. I actually believe the last 10 years, our practice of AI actually has going backwards from their program they set out. Because at that time, from that title of the book, right, they do not distinguish artificial intelligence and the intelligence of animals or human. They believe they're looking for the same mathematical and computational mechanism. Everybody, doesn't matter is it silicon-based or carbon-based, we're just different substrates to try to realize the same mathematical principles, right? So hence, I just ended this with this final quote from Richard Feynman, right? There is a chance we can deduce everything using deductive reasoning to understand deep networks, to understand intelligence, rather than has to do trial and error, try to do inductive way, right? So thank you very much. Sorry. We I think probably have a few minutes for, we started 5 minutes late. I can take a couple questions before we move on to the. It worked. I think it worked. Yeah.
Hi. Hi. Thank you for the great talk. I'm just curious. I have two small questions. So I know that it's well known that neural networks can fit to random labels.
Mm-hmm.
Does it? I'm just curious. In your experiments for the many papers that you listed, with random labels, do you still have well-performing networks that are able to achieve zero error or low error?
Absolutely, it's actually very easy, right? Because you only have finite samples in a space. You can arbitrarily assign samples. There's always a continuous map to map them to subspaces. Just like you can think about it, even fitting a one-dimensional label as a special case of what we're trying to do here, right? You map every class, whatever label is, you map to each one to a orthogonal one-dimensional line, right? One singleton. Here, you have even more freedom. You assign those points to a subspace. Right. So, well, be very easy.
Okay. So my second question is, what is the impact of the data distribution? Like if there's concentration or not less concentration, and how it's spread out over the manifold?
Oh, that's actually, as I said, this is completely right open, right? We may understand a little bit of how to even manipulate in the subspaces if the data, but if it's nonlinear manifolds, what's the density, sample density? I mean, that's going to be a lot of work. And how we can actually deform them correctly. What we actually wanted to what is the dynamics, controlling that dynamics from the curved to a straight? There's very little about it. Right now, okay, I can show you just the ResNet or a transformer just doing this, just try to all emulating the gradient, right? The gradient, the auto-regression gradient of that, and try to do that in a very greedy fashion. But of course, if you know more about the structure of the manifold, you can do much, much more efficient things. Maybe just take you a few steps rather than many steps, many layers to do that.
So if it works for random labels, then how complex the manifolds is does not really matter? Like you can still find maps to linear subspaces?
It's possible. It doesn't mean that you can do that effectively, right? There is a solution to map any data random label to a subspaces, but finding that mapping is a huge prize. You may not necessarily find it. You get stuck with local minima. Right? Something exists in something, and something that you can find it. That's two completely different concepts, right? You can compute it. That's different concept. All I'm trying to say is that right now we're just the ResNet or transformer. All this existing architecture is mostly just doing this in a very greedy brute force fashion. Yeah.
So in the start of your talk, you said that the correct solution, the optimal solution, is not always the correct solution. Mm-hmm. What is the correct solution here? You have a different principled optimization problem.
No, so basically the point is that if you basically the optimization, the network forward network, whatever it does, right? Even you have this object function delta R try to optimize. It doesn't mean that this network will converge to the right solution. We get stuck with local minima. Or in terms of the dimension, you could underfit or overfit, right? Maybe the apple, maybe the 5-dimensional manifold, the map to maybe blow up some noise, become a 6-dimension in the Z space, or kill some dimension you don't know about it. Right? So it becomes a 4-dimension. But in terms of that delta R itself, maybe you already reach local critical points. Right? You are done with optimization, but that solution is wrong. because it cannot faithfully regenerate the original source data. You have to check it.
So the definition of correct solution here is being able to regenerate data?
Yes.
Okay.
Yeah. You'll be able to establish a one-to-one mapping, right?
So I was wondering, so in the closed loop, does it seem like the encoder gets to have the last say? And is there like a symmetry between the, like?
No, that's why it's a game. It's an absolutely equal game, right? So F trying to maximize, try to remember Z, right? X as a Z, right? Make sure that there's no mistakes. And G is trying to regenerate X, right? So F is trying to maximize if there's any difference between X and X hat. G is trying to minimize X and X hat, so that the blue curve is chasing the black curve, basically, right? So they never actually to stop, by the way, right? Of course, if the black curve X is fixed, they maybe converge. If you correct the correct solution, you converge. But I'm actually arguing this process, this iteration, constantly sleep and wake, doing recognition, encoding, decoding, constantly using your memory to predict, it's more important than convergence. Why? What if X also changes? I drop you in a new environment, you have to recognize new objects. It's the same mechanism, start to loop. The loop start to remember things, to say if my memory serves me right. If there's any mistakes, I correct it. That mechanism is much more powerful than converging to some optimal solution. Right? I think we're very good at it. Right? Make the whole process completely autonomous. You don't need to do anything. As I said here, right? Just give one example at a time. All the things we do here, just give one sample at a time. And the network managed to remember all of them. And even if there's structure similarity among the samples, they start to show up in the Z space. And we don't know why. Of course, we can do further refinement, right? Nobody can stop you to doing that. Nobody can do backwards, can do whatever. But this is a mechanism to correct errors. It's very effective. And you don't have mode collapsing, you don't have neural collapse, you don't have catastrophic forgetting. Once you have closed loop. Probably maybe there's a reason why everything alive in the world is a closed loop. Nobody does backpropagation in nature, okay? The feedback loops are the sort of universal mechanism that correct errors, right? Check self-consistency, make sure there's no errors. My prediction matches with my observation. So see, I was trained as a control theorist, right? So, only when I'm almost 50 years old, I realized learning a memory, perception is by far the largest, the biggest control problem in the world, right? Not control our hands, our muscle, compared to this loop, nothing. The reason we can do this, we can do the muscles, because this gets trained. We already solved the largest control problem in the world, okay? Then we can control everything, right? Control your gesture, control your body, compared to this complexity, compared to this game we're playing. So your brain is constantly playing games. Hence, chess, Go is actually probably just something we picked up along the way. There's one more question. We are running out of time, but maybe one more last question. Hmm?
How do you remember, like you're learning a new skill, how do you remember it? How does it change the circuit?
Hello? Can you see that again?
Can you hear me? Yeah.
Yeah.
So if it is all feed-forward paths with loops, then how do you modify the circuit or remember new skills in your view?
Oh, that's why you have many, many loops, right? Loops after loops, parallel loops, different loops doing different part of the sensor or the data, memorize different things. They even have overlaps, right? So just remember this. My belief is that forward is always doing optimization, right? Error correction is always going by loops. Closed loop for error correction, forward for optimization. That's it, right? Forward, that's actually said also in recent paper from Hinton, right? The forward algorithm precisely said that, right? If you have a measure of goodness of your feature, the optimization should be done in forward fashion.
So in your abstraction, when we learn new skills, we are creating new paths, loops,
Yes. So you can see, the memory, perception is just one loop, right? Just the memory, right? But when you use that memory to predict what's going to happen in the world or what's going to happen with your action, so you learn the action, that's another bigger loop. You can use loop as a segment to build bigger loops. There's a perception is a loop, is a component, and there is a control part of your body, your muscle. You also learn that part. But that also forms a loop, right? From your eyes, hand coordination. Precisely, you have a memory to predict what's going to happen if you grab something, right? Then you learn that control. But that's another loop on top of big loop. It's a bigger loop on top of the loop of perception. Here, we only talk about the perception loop, right? How to build a world model for the memory for the world. We are not even talking about action, right? Use that for action, for prediction, for taking actions. That's another loop you can build. But what I'm saying is that loop is just a basic element, unit. You can do the parallel, just like our brain sheet. You can do it sequentially, right? Build more complicated systems. Okay, that's all. Yep. Maybe we should stop here and introduce the next speaker. Thank you.